Hi, it's me again. You'll never believe what happened. Here I am at school, and I had actually done most of this video that I wanted to show for you guys that I'm making right now. And the bell rang, my music came on, and I'm like, oh no, I'm gonna get a copyright strike if I don't erase this. So I didn't get a copyright strike, but I'm like, I have to do the whole video over again. Rip. So that's right. Maybe this time I'll do it a little better. So I want to talk to you a little bit about the geologic timescale in the history of Earth. Okay, so one thing, see, there's that bell. The music's over though. So I'm not going to give you information about the history of geology. It's actually pretty interesting. It wasn't taken seriously as a science subject until like the early 1900s. So apparently people didn't think that the Earth was that important. A lot of people thought the Earth was static, meaning unchanging for a long time. And people like the guy before, James Hutton. Oh, and there was another man. I can't think of his name off the top of my head, which is why I didn't want to talk about geologic history. Who are like, no, the Earth changes. There's like catastrophes and there's a slow, gradual movement. People are like, you guys are crazy. It's the Earth. It doesn't change. So again, this wasn't really taken seriously until like maybe 100 years ago. So, all things considered, geology is a new science, kind of a cool one too. So we're going to be talking about Earth history, like the geologic timescale. So how do we know how old Earth is? So first thing we can look at is relative age. So let me give you a couple examples. It's basically like, okay, well, we're not going to say how old the age of the rock is. We're just going to compare it to the layers around it. So like, for example, compared to me, you guys are young and I'm old. I'm not that old. But compared to someone like my dad, I'm young and he's old. So it's just like kind of comparing. Well, how's that going to relate to rocks? Well, with rocks and rock layers, the oldest layer we find at the bottom. I think of it like this. If you're just shoving papers into your locker or like a folder, where are you going to find the oldest papers in your locker? The ones from August. At the bottom. And that only makes sense, right? Because you got to put the ones from September, October, November, December up above them. They can't just float up there. So the oldest rock layers have to be formed first, and another layer has to form or get put on top of them, in general. So what do I mean in general? Well, there are times where the Earth moves. I mean, it's an earthquake. Like Earth layers move and change. The Earth is constantly moving and changing. We don't experience it that much because we're not on this planet for a long time, but our planet is always changing. If you could watch like a stop motion of the Earth from 4.5 billion years ago to today, it's always moving. It would look very active. We just don't live long enough to really see all that activity. So another example would be this law of cross-cutting relationships. If something crosses over these rock layers, well, you know, the rock layers had to be there before something to cross over it. So I think of something like this. If you see fresh snow or mud, and then you see a tire track in it, well, you know that the snow had to fall first, and then the car had to come because the tire track is on the snow. So like if lava intrusion is here over these rock layers, I mean, the rock layers had to be there. The lava's not just going to shoot out and like just kind of freeze in midair. It can't do that. So it's kind of like a puzzle for geologists to figure out. There's a lot of cool ones. And it's like fun to kind of puzzle out what came first and how did this happen. I'm not going to talk about fossils like that today, but you'll see some cool stuff in these notes, right? I told you it was cool. But we're not going to talk about fossils and fossilization and how things can become fossils. Not today. Not really. I might mention index fossils, but we're not really gonna do that. We're gonna focus on geologic time. So the geologic time scale is kind of like a calendar that scientists can use to sort of like, or a timeline to figure out, okay, well, what happened when, and kind of put a more serious date on it. Well, how do we date rocks? You don't be like, hey, rock, you want to go see a movie with me? No, I'm not interested. Let's just be friends. Oops. No. how we date things like rocks are through, I almost said radiocarbon dating. That's how we date things that are alive or were alive, living things. We use radioactive decay to tell us, and half-lives of these things to tell us. If I have us do anything with actually dating rocks of Earth, I will either make a video on half-lives or find a better video on half-lives to show you. So what about this? So when we have our radioactive decay, radioactive elements decay or break down in a very specific manner, and it's always the same. So we can measure it. So how do we do that? Well, let's say we're looking at these rocks. We might measure how much of the rock is there, how much uranium is there compared to how much lead is there. Uranium will decay into lead. So we can use that to kind of say, okay, this percent of the uranium has decayed. That means this many millions of years has passed. So that's how we do it. And we can get fairly accurate numbers doing that. And doing that, and on other evidence, we can estimate the Earth is between 4.5 and 4.6 billion years old. Scientists feel pretty confident about that. So let's kind of talk about like a geologic column. That would be like if we could get the youngest layer of rock that was made, and then go straight down to the oldest layer of rock that was made ever on Earth. Well, that doesn't exist. But there are places on Earth where we can find very, very old rocks and very, very young rocks. There are places on Earth where rock layers have been scraped away, and we don't know what they were like. We have an idea. We can compare them, but like maybe they were scraped away by glaciers and glacial erosion, or maybe there were floods or something that kind of have washed them away, or winds, constant winds that have like changed them. Like if you think of, gosh, like maybe you guys have never seen this, but like the Roadrunner and Coyote cartoons that have those like arches that's like out in the American Southwest, those were formed by wind. So we don't have like a complete rock layer like that somewhere, but scientists, geologists they've looked at rock layers all over the planet, and they've compared, okay, well, this rock layer is X number of years old. We see these fossils in it. This layer over here in China is X number of years old. We see these same fossils in it. These rock layers must have formed at the same time. Maybe they were even closer together. And we know that the Earth has been formed into like a supercontinent. During the time of the dinosaurs, it was Pangea. And if we go back in time before that, Pangea had to come together. So before that, it was in different pieces that don't look like the pieces today. And if we go back even farther, it was in a different supercontinent called Gondwana. So the Earth has changed a lot over time. And we can kind of compare these different rock layers in different parts of the world and say these were made at the same time. We see the same features. We see the same fossilized creatures here. So these must have been made at the same time. So once we've dated a lot of the rocks, we can kind of fill in the gaps and kind of get an idea of what was going on at the time. So it's all we have. Okay, it's pretty good. It's a pretty good measurement. It's not perfect. Not everything ever made a fossil. A lot of rock layers have been eroded, so we're not getting the whole picture. How do we divide up geologic time? Why do we have these different eras? Well, we divide them by clear changes that have happened in the rock layers and in the fossil record. And when we kind of measure this, you might see these symbols, MYA or BYA. That means millions of years ago or billions of years ago. Just you'll probably see it. Doesn't mean Maya. It's not someone's name. It means millions of years ago. So all this stuff is usually divided by clear changes. And what I mean by that are things like extinctions. Like we say the dinosaurs died out 65 million years ago. That's because after that time point, about 65 million years ago, we don't see fossils of dinosaurs at all anymore. They're gone. They're not in any younger rock layers. So something must have happened. And so we would say, okay, well, that's the end of this eon, for example. So here's a timeline. This one's not very good because there's not a whole lot of stuff on here. We're trying to put 4.5 billion years ago on a line this big. It doesn't impress upon you how short of a time humans have been here. Let me tell you something that has stuck with me since I was a young girl. When I was really little, I really badly wanted Nickelodeon magazine. If you're bored, look up 90s commercial for Nick magazine. It was on all the time. I wanted those magazines so much. And my parents one time got me Nickelodeon magazine. I was hyped. I was so excited. I can't even tell you. I was much younger than what you guys are right now. But so I was very excited. In one of these magazines, I remember reading about, like, they talked about dinosaurs and they talked about time. And they said, what if you shrank? Oh, yeah. Are you guys in dress code? I got to make sure to take attendance. That's what that is. So they said, what if you shrank all of the history of Earth, all 4.5 billion years ago, into a school day from 8 to 3, like our school day? How long would everything be around for? And what really stuck with me is human beings wouldn't have been around until 2 o'clock, 2:59 and 59 seconds, probably even a little bit after that. Probably literally less than a second before the 3 o'clock bell would ring and you get dismissed. So human beings have been around on Earth for like no time at all. The dinosaurs were around way longer than what we were. They'd show up, they'd go to ISS. I mean, I think of a dinosaur, I think of him probably causing trouble. They'd go to ISS, and then they'd show up in fourth block, somewhere in there, just to like be in there, and then they'd leave probably at like 2:30 and be like, all right, see you guys later, see you tomorrow. But not really, because we're going extinct. And then they'd be gone. But they were around this planet longer than we are. You could, if there was aliens, we could think they would call us the planet of the humans. But we're more like the planet of the dinosaurs. They were around way longer than we are. So this timeline, this particular one, not a very good one. Let's take a look at some better things. So we're going to divide geologic time. The eons are the largest of the geologic time scale units. And the first 3 eons, we divide those up and we just call that the PreCambrian era. It means before the Cambrian era. Thanks. So why? You'll see. We say that there is this Cambrian explosion where all of a sudden in the rock layers we find fossils of like tons of sea creatures. So like that's like kicked off like, hey, life on Earth is like busy. Like there's a lot of stuff going on. But look at this cool stuff. Can you imagine? We have Precambrian fossils of creatures. And we're like, what did this look like? We have no idea. There are very few fossils from this time, and it's very hard to form into a fossil. It has to be like kind of perfect conditions for a creature to be fossilized. And if they don't really have lots of hard body parts, they're not going to really make a good fossil. So, I mean, imagine if you could take a time machine and go back and look. Wouldn't that be cool? Man, can one of you guys invent like a time machine and like help me be able to see these creatures so I can have my mind blown? Anyway, so if you're interested in like creatures on Earth, we don't know what they are. Well, here's some, and then do a little bit more digging. Also, let's say thanks to these guys right here. These are stromatolites. You can still find these today. They form into they're almost like living stones. They're not, or they're like a little reef. Like this is in Australia. We owe a lot to these guys. You're here because of them. They're bacteria, so they're prokaryotic cells. They form into these mats. So you'll have like a layer of these cells. They'll divide, and the next layer will kind of form on top, and then this will die, and they'll kind of form into this hard rock-like. It's not a rock, but like thing. So these are some of the first creatures that we know of. They're stromatolites. They were photosynthetic. So they created the oxygen that exists on this planet today. So 3.5 billion years ago, these things were turning sunlight and water and CO2 into food and oxygen. And that's the oxygen you're breathing now. How cool is that? I know you're like, Miss Helen, that's not cool. Yes, it is. Yes, it is. Okay. So we've got the next kind of unit we can divide into are things called eras. And an era is a unit of time that's going to include 2 or more periods. So we're kind of just dividing time into smaller and smaller small bits. So the Phanerozoic eon we can divide into 3 eras. Okay, the Paleozoic, the Mesozoic, and the Cenozoic. And different fossils are represented in each of these eras. Okay, so we can see sea life, birds and reptiles, mammals, that sort of thing. So in the Paleozoic, man, this is when we start to see this explosion of life. The first time period in this is the Cambrian time period. Okay. Oh man, like we see such cool, crazy creatures. Right before this, the Earth was sort of like this ball of ice that we thought nothing could survive maybe, but life in the oceans had survived under this thick layer of ice that was around on the planet for millions of years. So in the beginning, all life here at this time in the Paleozoic was in the oceans. And then as we move forward through time, that's when we start to see things kind of slowly move on to land. And we start to see like trees and stuff. Before this, there wasn't a whole lot on land. There couldn't be a lot on land because we had no ozone layer. Remember the atmosphere? So because there was no ozone, like it wasn't safe to just be on land. You would get hit with ultraviolet radiation that would damage your DNA. That could cause things like cancer. So things really couldn't pop up on land for long periods of time. But this is the time when our ozone layer had formed. We start to see trees and we start to see land creatures. So the Paleozoic was a busy time. Then we have this Devonian period. That's like where like it's a period in this age or in this time period. Oh my gosh, that's when you start to see all these fish like Dunkleosteus. Oh man, like so a lot of like busy stuff happening in the oceans. Then we have the Mesozoic. That's the age of the reptiles or like the dinosaur age. So that's like actually I found out something neat about Dimetrodon. I was researching it for bio in the first semester. Here's my Dimetrodon, colored by Thomas. Here's something interesting about Dimetrodon. It's not a true dinosaur. It was there before the dinosaurs, and in fact, things like Dimetrodon, their kind of line led more to mammals than reptiles and birds. What? Isn't that crazy? Like you might be more closely related to Dimetrodon than to T-Rex. I love all this. So the Mesozoic we can divide into periods. The Jurassic, Triassic, and Cretaceous period. So dinosaurs ruled the earth at this time. They say Jurassic Park, but really, like a lot of the creatures they had at that time were from the Cretaceous. So like this, there's a mix of like Cretaceous, Triassic, and Jurassic animals. And the Cenozoic, that's like what we are now. That's the age of mammals. So after the extinction of the dinosaurs, mammals kind of started to be the ones that sort of were prevalent in the fossil record. And towards the end of the Cenozoic, we show up. Here we are. Sorry, everything's backwards. So, eras, like, can be divided into shorter periods, time periods, literally called periods. Each period is characterized by the fossils, and they're named for where they were discovered. So, like, my head is blocking, like, Mississippian and Pennsylvanian periods. And then when we have such a complete fossil record where we have accurate information about this, we can divide it into an epoch. So we're here in this quaternary period, all the way up at the top where my mouse is. That's us. We're in this Cenozoic era. So there's the Mesozoic, Paleozoic. So we're currently here in the Holocene epoch, where it's named after us because we've started to really have a huge influence on what's happening on the earth. And you can really see that if we disappeared during this time, you would see human beings mark on the planet. You would see our fossils and stuff, so you would see us. So if we start now, and we can kind of go backwards through geologic time, Okay, so this is going backwards. So like the Precambrian, where my head is, not a whole lot's going on there. There's not a whole lot of life there. That's why it's kind of left blank a lot. But lots of really interesting things going on. So here we have all of this geologic history kind of up here, and it's kind of trying to show us, as we go through rock layers, we start seeing different fossils. And as we go through and see these different fossils, it kind of marks off these different time periods. Like for example, trilobites. Oh my gosh, they were around all through the Paleozoic. But we can definitely see them prevalent and certain types of them in certain periods. Like we would see them start off in the Cambrian. What else? Oh yeah. So speaking of trilobites, they're like the ancestors. You'd be like, that looks like a horseshoe crab. Yep. They're also related to like all insects and things like lobsters and crabs. Like they're all kind of related to those. Those are like the arthropods. So see right here, this TK boundary and this TP boundary, where we have the boundaries between these eons. There was a huge extinction event. There have been multiple mass extinction events on the history of the Earth, and scientists now say that here at the top, we're in another mass extinction event, and this one is caused by human behaviors. That's what's going to kind of mark this Holocene epoch. There's going to be like these mass extinction, hopefully not, but it'll be kind of whoever in the future will see in these rock layers creatures all of a sudden disappearing. And a lot of that is caused by us. Oops. So I wanted to kind of just go over some of these quickly and kind of show you guys some of these different time periods, because you're going to make a geologic time scale. You're going to do some research, and you're going to work with other people. You're going to make a big long timeline, and you're going to kind of map that out and show what's going on, and draw some things that existed at these time periods, and kind of show how little of a time we have been here. It's really little. It's like nothing. So I think that'll be like interesting for you guys. You'll have that stuff, and I want you to work together. Use some big giant paper and measure it out and make something huge. I don't know what we'll do with it. We got to hang it up somewhere. I think that's what needs to happen, because it's going to look great. So this is a more traditional looking geologic time scale. So here's our Precambrian with our Archean and our Proterozoic eons. And then we're currently in the Phanerozoic eon. And so these things can kind of be divided up into late, middle, and early, depending on how old the rock is. What we do see, rock formations, what kind of weathering or erosion you might see on those. So let's take a look at these eras, because this is where most of our life has come from. Paleozoic, that's stuff that maybe you wouldn't think totally about. That's where we had a lot of creatures living in the oceans. So we see all those trilobites and lots of like really cool things. And the Cambrian is what the Cambrian subperiod. Boy, that's where we start seeing all life and fossils really start. Do we see fossils before that? Yes. But before about 544 million years ago, not billion, not life on Earth has only been really like here and like super present and like very clear that the Earth is full of life for about 544 million years. The Earth is 4.5 billion years old. So for almost 4 billion years, there was life on Earth at some point, but it was like tiny, single-celled, wimpy. Like maybe there's like worms and stuff, maybe a mushroom. Not wimpy, because like they were here and they're kind of related to us. And by kind of, I mean they are. But we didn't see this huge explosion of life until the Cambrian. Okay, so as we go through the Paleozoic era, we can see changes from just being like ocean creatures to things starting to come up on land. Then we enter the Mesozoic era, and that's what we like think of as the era of the dinosaurs: Triassic, Jurassic, and Cretaceous. That's what you would think of, the time of the dinosaurs. So Triassic, we'd see like early dinosaurs, things like Stegosaurus. Jurassic, you'd see things like, I gotta think about that. I mean, you'd see like pteranodons and stuff. Probably you'd see like, I'm trying to think, because all the things that I think of right away are in Cretaceous. Like T-Rex was a Cretaceous creature. Spinosaurus was a Cretaceous creature. My Spinosaurus tooth, wherever it is. Hold on, this is important. We got to find it. Here it is. Don't worry. No, you were worried. This is 99 million years old. Ignore the crack. That was my lovely and beautiful daughter. She wanted to look at it and dropped it onto carpet. It's delicate. Okay, it's 99 million years old. Happy birthday. But those creatures that you're thinking of are Cretaceous creatures. So, like, I guess Cretaceous Park doesn't sound as cool as Jurassic Park. But then what happened? Well, there was that extinction event that killed off a lot of the dinosaurs. A lot of the dinosaurs were specialized, ate special food, only ate certain plants. If those died out, well, then the dinosaur died out. And if, this dinosaur only eats that other type of dinosaur, and that one went extinct, well, guess what? You're going extinct too, unless you're adapted or are able to eat something else. And if you're not, you will go extinct. So we saw a large extinction event in the Mesozoic era at the end of the Cretaceous. That was about 65 million years ago. And now we're in the Cenozoic era, where we're in the time of mammals. So that's when you start to see mammal fossils. There were mammals before this, but that's when you start to see the rise of more mammal fossils. So those are like the kind of things that mark these changes in these large eras right here. Sea creatures, reptiles and birds, mammals. Okay, so that's the kind of thing. And then these things can kind of be divided up, and we're way up here. One thing I don't like about this time scale, take a look at these numbers. On a graph, if you space out these numbers, they should be equal. These are not equal. So this time scale isn't great. You're going to make a more accurate one. Okay, but that means we got to make something big. Okay, and that means some parts of it are going to be large and blank and kind of empty. But that also means other parts of it are going to be like little and tiny and, I don't want to say crammed in, but kind of crammed in there. So that's what you're going to be doing. You're going to make a more accurate time scale, as in these numbers are going to be equal. Look, we're going to 3.8 billion, 3.8 billion years ago to 554 million years ago. So we went like 3 billion years in this little spot. And in the same amount of distance, we haven't even gone 100 million years. Not accurate. We're going to make something more accurate so you get an idea of how long the Earth has been around and how short we've been around and how short everything else has been around. Because it's a good thing for you guys to see, like, the history of Earth. So I hope that kind of helped go through some of these. I will try to find some links for you guys to other geologic timescale videos to help you understand and put into perspective everything. But really look it up. Like, oh my gosh, the history of the Earth, amazing. Maybe I'll have you guys watch this one video I really like about it and have you respond to it. I got to think about it. So I hope it helps. I hope that you will enjoy working on this geology timescale. And I will see you later. Bye.